Good morning, good evening, good night, good day, and welcome to MIT Innotherm Colloquium number 9. I'm Gang Chen, and today we have a very exciting talk on hydrogen. And I just learned from Professor Ogazaki, actually there are over 280,000 deployment in household of hydrogen system, the fuel cell system in Japan. That's really amazing. So we have a very exciting panel consisting of Professor Majunda and Professor Takata. And the moderator is no stranger. And so let me just introduce Jun again, and he will introduce the rest of the speaker and the panelists. And Jun is currently the department head at Mechanical Engineering Department, University of Tokyo, and he's also visiting researcher at the Rankin Center for Advanced Intelligence. And his research area in nanoscale heat transfer, interfacial dynamics, thermoelectrics, materials informatics, multi-scale computing. And I also had a great pleasure working with Jun before. And with that, let me turn to Jun, and you can take it over here from here. So I'll stop sharing my screen.
Thank you very much, Gon. Let me share my screen. Okay, so my great pleasure to be back as a moderator in this colloquium. And I would like to, first of all, thank the organizers at MIT, led by Professor Gan Chen. Today, as Gan said, we have a very exciting topic on hydrogen energy. And the presenter today is Professor Ken Okazaki. Hold on. Professor Ken Okazaki. He's a currently Institute Professor Emeritus of Institute of Innovation Research at Tokyo Institute of Technology. Formerly, he has been the Dean of School of Engineering at Tokyo Institute of Technology and President of Hydrogen Energy Systems Society of Japan and Heat Transfer Society of Japan. And he was also Vice President of Japan Society of Mechanical Engineers and also official member of the Science Council of Japan at the Cabinet Office. His research areas include hydrogen-based advanced energy systems and fuel cells, clean and high-efficiency coal and biomass technologies, non-equilibrium plasma chemistry and applications. We also have two great moderators today, panelists today. The first panelist, not to mention, is Professor Arun Majumdar. He's currently professor at Stanford University in Mechanical Engineering, Material Science, and Photon Science. He's also co-director of Stanford Precourt Institute of Energy. He was formerly founding director of RPE at U.S. Department of Energy, acting under Secretary of Energy, U.S. Department of Energy, Vice President of Energy at Google, professor at University of California, Berkeley, and he's been a member of these organizations. His research areas include electrochemical and thermochemical redox reactions, nanoscale heat transfer materials and devices, energy conversion, transport and storage, biomolecular analysis, and nanoscale imaging and microscopy. The other panelist is Professor Yasuyuki Takata. He's currently professor at Department of Mechanical Engineering, International Institute of Carbon Neutral Energy Research, Eisner, at Kyushu University. He's also vice president of Asian Union of Thermal Science and Engineering. He was formerly president of Heat Transfer Society of Japan and also president of Japan Society of Thermophysical Properties. He's been awarded, received many awards in the research areas of hydrogen thermophysical properties at high pressures, effective surface wettability on liquid vapor phase change, and heat transfer enhancement of boiling and evaporation. Okay, before we move on to the presentation, I would like to remind you about the format of this colloquium. Here's the agenda of today. We'll ask Professor Okazaki to give about 40 minutes presentation.
Yeah.
And that will be followed up by 30 minutes or so discussion before we wrap up. Meanwhile, right after I finish talking, either during Professor Okazaki's talk or during the discussion, you're very welcome, or please do, ask questions. When you ask questions, please use the Q&A button in Zoom, and we will be pulling from that stream the questions. Questions are visible only to the panelists, not to the other attendees. Please also submit any suggestion you have for future topics and speakers. And note that this colloquium is being recorded and will be posted on YouTube later. This may also include questions which we can't get to today. And when you ask questions, if you prefer your question to be anonymous, please state so in your question. Otherwise, we'll be calling your name. Okay. One more thing before moving on to the presentation. I would like to make an announcement for the next colloquium, next webinar, which is on 19th of August, the same Wednesday, same time. It will be about thermal management of electric vehicles, new engineering challenges. Let me also mention about the future events. This is on September 2nd. The topic will be Earth's energy balance. Okay. So with that, I would like to introduce Professor Okazaki, or I would like to ask him to give a presentation.
Yeah. Let me
Okazaki
share.
Sensei, yeah,
Yes.
the screen's all yours, please.
Can you see that?
Yes, we see the screen.
Okay.
But do you want to
Okay.
do this? Yeah.
Okay. Thank you so much for introducing me. Hello, everybody. My name is Ken Okazaki of Tokyo Institute of Technology. First of all, I'd like to say thanks to the organizers, especially Professor Gan Chen of MIT, to give me this kind of opportunity. Basically, I like the fundamental researches, but today I'd like to talk about an overview of hydrogen on the significant role of hydrogen toward SDGs, Sustainable Development Goals. The outline of my talk today is why can hydrogen contribute to SDGs, and Japan's history of hydrogen and fuel cell technologies, and basic hydrogen strategy and roadmap in Japan, and various R&D activities for hydrogen energy, and global scale CO2-free hydrogen supply chain, and world trends including Germany, EU, US, and China. And finally, I'd like to mention about the fundamental researches related to heat and mass transfer coupled with electrochemistry, and concluding remarks. As shown here, hydrogen is secondary energy and can be produced from various different kinds of energy resources, including domestic fuel cells, overseas unused energy, and renewable energies. Especially renewable energy is the most important to produce hydrogen in the future. And hydrogen is transported to the demand side and to be used to realize the CO2-free industry and CO2-free mobilities. This slide shows the renewable energy, situation of renewable energy in Japan. At present, the percentage of renewable energy is only 12% in Japan, but we have to increase this percentage to 22 to 24% by 2030, including solar power, wind power, biomass, and geothermal. Especially in Japan, the solar power, PV, will play a very important role. Here we discuss why hydrogen now. Because of clean energy, flexible energy carrier, and long experience in hydrogen development in Japan. But when we discuss about the energy security and global environment, global environment, hydrogen should have a large, massive contribution. And another importance of hydrogen is that hydrogen can enhance to introduce more and more renewable energies, because renewable energy, especially natural energy, has very large many fluctuations from seconds, minutes, hours to seasons. So for the load leveling for that, the hydrogen will play a very important role. Now another one is the large electricity production above demand. In this case, the hydrogen can store much amount of energy for long term. Battery may have a same role, but energy storage capacity and the duration time are much smaller than hydrogen, as shown in the next slide. As shown here, hydrogen has a very large capacity corresponding to 1 gigawatt and can store energy for long time corresponding to this minute, hour, day, week, and even seasons. So hydrogen will play a very important role when we introduce more and more fluctuating renewable energies. Here, I'll mention about Japan's history of R&D in hydrogen and fuel cell technologies. We have more than 30 years experience for hydrogen and fuel cell technologies. 2009, we introduced the household fuel cell, PFC, and 2011, we introduced household fuel cell, SOFC, and 2013, we introduced the hydrogen refueling stations and dissemination of hydrogen stations. And as you know well, the actual commercialized fuel cell vehicles sales started 2014. And now the global hydrogen supply chain and hydrogen power generation are now going on, including various demonstrations as explained later. As for the national strategies, basic hydrogen strategy was established about 2.5 years ago, December 2017, declared by Prime Minister. And among them, hydrogen cost is the most important. The target is shown here, $3 per kilogram hydrogen by 2030 to $2 per kilogram hydrogen by 2050. And to realize that, the large-scale hydrogen supply chains and massive usage of hydrogen in mobility, power generation, and industry general. And key technologies to be developed are shown here. In the production, the electrolyzer system is quite important, and transportation. For the transportation, which kind of energy carrier should be used, and the utilization part, our demand side, fuel cell for mobility and power generation, and hydrogen-fired power generation will be quite important in the future. This is the scenario for basic hydrogen strategy. As for the hydrogen volume, this is a present picture, and this is the target by 2030. As for the hydrogen volume, the target in 2030 is about the 300,000 tons per year, and the cost should be $3 per kilogram hydrogen, and the power generation cost, it should be the 17 Japanese yen per kilowatt hour, which corresponds to the 15 cents per kilowatt hour. And for the mobility, hydrogen stations, 900 should be introduced, and 8 FCV, fuel cell vehicles, should be introduced. 800,000 fuel cell vehicles should be introduced. And utilization of fuel cells for the household, in private houses, should be 5 million units by 2030. So we are now going on to realize such kind of target. By the way, what is the definition of hydrogen society? I myself said about 3 or 4 years ago as such like this: a society where hydrogen used as a secondary energy accounts for over 20% of all energy consumption, including the industrial applications, and hydrogen quantitatively and sufficiently contributes to energy security and carbon neutral society. These are the two major issues to realize such as hydrogen society. One is the domestic expansion of demand, including fuel cell vehicles, residential fuel cell cogeneration units, and hydrogen electrical power generations. And for that demand, we have to realize the supply chain for a large amount of hydrogen. One is CO2-free hydrogen derived from domestic renewable energies through P2G, and also CO2-free hydrogen from unused energy from overseas. So increase of demand and supply, both are quite important. This kind of 20%, this value was supported by the Hydrogen Council next year of my proposal. Maybe all of you know well, but here I'll show briefly about the principle of fuel cell like this. This is a membrane, and this is the fuel cell, and this is MEA, membrane electrode assembly, and fuel cell stack. More than 300 fuel cell MEA gathered in the one stack, more than three, I'm not sure, but more than 300 cells will be packed in the fuel cell sack and installed in the car. This is a high pressure hydrogen tank. Pressure is 70 megapascal, corresponding to 700 atmospheric pressure. Such kind of high pressure hydrogen tank is just below your rear seat. Many people may be interested in the comparison between battery EV and FC EV, in between hybrid EV and plug-in hybrid EV here. FCV, fuel cell vehicle, has an advantage, especially for large vehicles, including buses and trucks, considering cruising distance and charging time. For the fuel cell vehicle, hydrogen refueling time is only 3 minutes. Much longer time should be necessary for the charging of battery EV. This slide shows the status and target of fuel cell vehicles in Japan. I already explained the target of introducing fuel cell vehicle is 800,000 by 2030. And by 2020, we tried to introduce 40,000 fuel cell vehicles, but actually, can you guess? Actually, 10,000 fuel cell vehicles. That's behind our target. And fuel cell buses are also introduced into public services. Another important system to use hydrogen is the stationary fuel cell system, stationary fuel cell cogeneration systems. City gas is reformed to form hydrogen and CO2. And hydrogen is used to form electricity and heat or hot water through the fuel cell systems and supplied to the houses. Now we have 280,000 units are already introduced into the private houses, including my house. I introduced this kind of system in my house about more than 7 years ago. This is the ongoing project. As for the mobility, I explained already, but as for the hydrogen power generation, the hydrogen cogeneration demonstration project was the demonstration has been successfully done 2 years ago in Kobe area using hydrogen gas turbine system of 1.7 megawatt. This is, of course, a cogeneration system. And electricity is supplied, and heat is also supplied to surrounding hospitals, athletic gyms, and others. The other big project is to develop the large-scale hydrogen combustion gas turbine. This is an example to develop the burner system. As you know, Japan has almost no energy resources. So to supply a large amount of hydrogen, we in Japan are developing global scale hydrogen supply chains. Two are almost come to the demonstration stage. One is using the associated gas reformed to form hydrogen to make MCH, methyl cyclohexane and transported to Japan. The other one big project is using the lignite of Victorian state of Australia to make hydrogen and liquefied and then transported to Japan by the liquid hydrogen tanker. I'd like to explain a little more ongoing project. This is the Brunei project I explained. This is the Japan-Australian project, pilot project. Brown coal is gasified to form hydrogen and CO2. CO2 is transferred to the CCS process. CCS means carbon capture and storage under the ground. So CCS process. And the liquefied hydrogen is transported to Japan by hydrogen tanker to the demand side. Okay. So in this case, we can realize no CO2 emissions, even though we use the coal. Another one big project, domestic project in Japan, is the Fukushima Renewable Hydrogen Project, using the PV, photovoltaic power generation, to form the hydrogen, and electricity is used to make hydrogen through electrolyzer. And hydrogen is planned to transport it to the Tokyo area to be used for Tokyo Olympic Games, but it is postponed or cancelled now. Next slide shows a diagram of this kind of systems. This slide shows the pilot scale, the liquid hydrogen tanker, like this. And the commercialized scale is shown here by 2030. But this kind of shape is not a dream. Actually, we realize this kind of liquid hydrogen tanker and world first liquefied hydrogen carrier, so-called Suiso means hydrogen, Suiso Frontier. Launching ceremony was actually held in December last year, only half year ago. So, as shown here, we have come to this kind of actual stage. At present, hydrogen still play an only small part in the energy sectors. To expand hydrogen utilization, various factors as shown here are necessary, such as large-scale hydrogen supply from abroad and large-scale utilization of hydrogen in various industrial sectors, including electrical power generation, oil complex, industrial applications, city utility, and transportation, hydrogen station, cogeneration, and zero-emission buildings. For that, these kind of challenges are definitely necessary, including big investment, especially big investment and cost down of hydrogen price, definitely necessary. To accelerate such kind of accelerate the implementation, this kind of trinity among policymaker, industry, and the financial sectors necessary. In Aichi prefecture is actually promoting this kind of initiative by a collaboration of Aichi prefecture and the energy companies as shown like this. This is the Aichi low carbon hydrogen supply chain 2030 vision by the collaboration among Aichi Prefecture, energy companies, and also big Toyota. Headquarters of Toyota is in the Aichi Prefecture. And the first stage, this is the target is the expand renewable energy-based low-carbon hydrogen supply chain using the existing infrastructures like this. So first stage, we already realized sustainable development of low carbon hydrogen supply chains and using the biogas and transported to the usual existing city gas pipelines to the Toyota factories and used to supply hydrogen to the forklifts. And second stage, low carbon power, transport, heating, and industrial processes in every field like this. And finally, the elimination of reliance on fossil fuels through greater distribution of hydrogen over wide areas like this. We are now on this stage. And I am also chair of this project. As for the national hydrogen strategies, this is an example of the Germany national project, national hydrogen strategy in Germany. They are, of course, also considering the combination of large introduction of renewable energy and green hydrogen. So surprising is the budget size. Budget size is 9 billion euro for hydrogen, corresponding to 10 billion US dollars or 1 trillion Japanese yen. Which correspond to the 7% of total budget of economical recovery after COVID-19. And hydrogen production by electrolyzers, 5 gigawatt by 2030 and 10 gigawatt by 2040, like this. As for the United States, the famous national project, so-called hydrogen at scale energy system, operated by the DOE. Arun was one of the panelists, was number 2 or number 3 of DOE before. The important thing is matching among energy sectors, electrical grid, and hydrogen generation, storage, distribution, and utilization, including industrial applications. The concept is almost similar like others. As for the, about China, this is also surprising. This slide was given to me by the leader in hydrogen in China, Professor Mao in Tsinghua University. The total budget for 2 years, 2017 to 2018, the 230 billion yuan correspond to 30 billion US dollars and 3.5 trillion Japanese yen, 3.5 trillion yen. So not only in Japan, as shown here, not only in Japan, but also Germany, United States, China started to realize the hydrogen society. Finally, I'd like to mention about the fundamental researches related to heat and mass transfer, including the fuel cell, and electrolyzer. I don't have enough time to explain the details. Fuel cell and electrolyzer, and hydrogen oxygen combustion and turbine system, and distributed cooperative energy system, and hydrogen carrier and supply systems, including the physical properties of liquid hydrogen, including the ortho-para transitions. Yes will mention about this later, I think, and many others, including fundamental physics, chemistry, thermodynamics, very important research subjects still play a very important role to realize the hydrogen society. Some example we did in Tokyo Tech shown here. This slide shows the Tokyo Tech interdisciplinary research project on PEFC polymer electrolyte fuel cell with higher energy efficiency and durability in collaboration with mechanical engineering, electrochemistry, catalytic chemistry, and polymer science like this. So we did this kind of collaboration among various different among professors of different research field, different background. This is also one example I myself did many years ago. I used the molecular dynamics to calculate the proton transport in the membrane. And also I did the first principle analysis for the surface catalytic reactions for polymer electrolyte fuel cells like this. Now this is the old one, but my background is mechanical engineering, but we submitted this kind of result to the Journal of Electrochemical Society like this. But this is the old one, and now much higher stage of research are now going on by many researchers, including the mechanical thermal mechanical engineering field of thermal engineering field. Another topic is like this. Another example is a new cycle of hydrogen and pure oxygen combustion gas turbine. Combustion product is only steam, and then the simple hybrid system of Brayton cycle and Rankin cycle could be possible like this, as shown in this temperature entropy diagram. As shown here, very high efficiency could be realized in principle, but we need many fundamental researches to realize that. So we are now starting this project supported by NEDO. Finally, I'll say about the concluding remarks. Hydrogen has a high possibility to realize energy security and zero CO2 emissions. The energy and the environmental sectors of SDGs, Sustainable Development Goals. And Japan has 30 years history of developing hydrogen and fuel cell technologies, and the basic hydrogen strategy and roadmap has been established. R&D of hydrogen technologies are remarkable in Japan, and fuel cell vehicles and stationary fuel cell cogeneration systems have been already commercialized. Demonstration of hydrogen gas turbine system for power generation and cogeneration are going on to realize a real hydrogen society, including the industry. And various challenging projects are now going on using CO2-free hydrogen from renewable energies. We still have many fundamental scientific research subjects related to heat and mass transfer with electrochemistry. That's all my presentation. Thank you very much for your kind attention. Thank you.
Thank you very much, Professor Ken Okazaki. That was a really great talk. So now we want to move on to the discussion, but before doing so, I would like to suggest to do a poll. Actually, I was supposed to do it before Ken's talk, which I forgot to do. So I'm going to do it now.
That's okay.
Sorry about that. So here's the poll. Okay, so do you see this? I guess everybody sees it, or maybe not. I guess, do you see it? Yeah, okay, people started voting, so I think you see it. So at present, hydrogen plays only a small role in the energy sector. What is the most important factor for a wide use of hydrogen's energy? So there was actually a question related to this poll. So I think this poll is quite timely.
Yes, yes.
Okay, so we reached already half, 50% of the people already answered. %. Let's give it 30 more seconds, or maybe 15. Okay, thank you very much. We're going to end the poll here and show you the result. Okay, so here's the result. 34% of people voted for hydrogen cost. And then the next one is technology innovation. Follows national strategy, investment, and public outreach.
Okay.
Shall we do the other poll also now? There's a second poll.
Yes, but I'd like to mention something about
please do, please do.
Okay.
Great.
Yeah, I talked in every point in my talk. So, but the result is very correct. Hydrogen cost is the key to realize the hydrogen society. And to reduce the cost, innovative technologies are definitely necessary. So I agree this result. John, please
yes.
Do the next poll.
Sure. Okay, so I'm going to do the next poll. All right, how do I do the next one? No, hold on. Let me do
this is
again.
the first one.
Yes. Yeah, here. I'm sorry. Okay. So this is the second poll. What is most important when we discuss the different roles between battery-driven electric vehicle and fuel cell-driven electric vehicle? I think a lot of people are also interested in this question. So please start voting so that we know what you're thinking now before the discussion, so that the panelists can elaborate on this during the discussion. Okay, so we have already reached 71%. We can close it almost. Okay, so people are still voting. All right, okay, let's stop it here and let me share the result. Cost and lifetime, 37%, and 34%, very similar. Charging time and refueling time.
Okay.
And then others are answering size and cruising distance.
Yeah.
All right, maybe we can go around the, Ken, maybe you can start making comments on this.
Yeah, but those items depend on the different standpoint. Both fuel cell vehicles and battery vehicles, both are very expensive now. Okay, But I think the charging time and the refilling time, hydrogen refilling time, so much different. 3 minutes and 3 minutes and 30 minutes, and a very large difference. So this result, I almost agree. But how do you think, John?
Or we can ask the panelists. Arun, do you have any comments on these? Oh, you're muted. I think you're muted.
Good. Can you hear me now?
Yeah.
Good. First of all, it's great to be on a panel with my old friends, Ken Okazaki and Yasu Takata. We have been friends for many, many years now. And also congratulations to MIT for launching this and continuing with this. It's a great forum to kind of discuss details of issues that we all care about. The issue about the battery versus hydrogen fuel cell for transportation, there are multiple ways to dissect this. I can tell you about the US side, the long-haul trucking, which requires the trucks to be on the road as much as possible. And for fast refueling, there is significant interest in hydrogen, but hydrogen will have to compete with battery long-haul trucking as well. The gravimetric energy density of hydrogen is very high. And so if you're looking about loads and carrying capacity of trucking, that makes a lot of sense. And these are centralized facilities for refueling, and that makes a lot of sense. At least in the United States, for light-duty vehicles, the battery electric vehicles, the infrastructure for distributing electricity already existed. If the electricity distribution infrastructure did not exist before, I think battery electric vehicles would have had a really difficult time. But that already has been around for the last 100 years. And so refueling is, and you don't need fast refueling of battery, too often. And so you can, stay at home and get it charged overnight. And most of the charging that we are going to see, and if you talk to the folks in Tesla, for example, they'll say most of the charging is level 2 charging, which is roughly about 10 kilowatts or so. And that's adequate for most of the charging for light-duty vehicles. So I think in the light-duty area, the battery electric vehicle is going to play a very dominant role in the United States. So I think you see the different parts of the transportation sector adopting different technologies for given the economics and just the logistics of things. So I think that's where we see things going in the US.
Thank you. Yasu, do you have
Yeah. So yeah, I'm a little bit surprised with two quick polls about the same answers. The majority is many people are thinking cost. Okay. But regarding the charging time and the refilling time, so Ken mentioned that currently the fuel cell vehicle needs only 3 minutes to refill the hydrogen. But the former time, so the hydrogen tank pressure was 35 megapascal. At that time, the cruise range was not so long compared with a gasoline car. Then so tank pressure increased up to 70 megapascal. Now maybe 80 megapascal or something like that. So then when we refill the hydrogen into the high pressure tank, so adiabatic compression occurs and increase the temperature. Therefore, currently the maximum limit temperature is 85 degrees Celsius. Therefore, so before refilling the hydrogen, so we have to cool down the hydrogen in advance down to minus 40 degrees Celsius. Okay. That's that's why the hydrogen refueling station becomes very complicated, and it's not easy to reduce the cost. That is my observation about it.
Okay. Thank you. Jun, can
Yes,
I say
please
something?
go on. Of course,
Okay.
of course.
We are just discussing about the mobility, the hydrogen utilization for mobility. But as I said in my talk, the hydrogen is more important in the industry to realize the CO2-free society. Okay. Only the mobilities share only 10 or 15% of total energy consumption. Others, most of energy consumption is done in industry. So large-scale power generation using hydrogen, large-scale some kind of power generation of the fuels, using fuel cell, and the larger one using the hydrogen turbine. Even the hydrogen boiler can reduce the CO2 emissions. Okay, so large-scale hydrogen consumption system will be more important when we realize a CO2-free society using hydrogen. I'd like to ask some opinion about that, Arun.
Yeah, I mean, look, today there's a global production of about 70 million tons of hydrogen globally per year. Almost, there's a large fraction of that goes into ammonia production, which goes into fertilizers. We eat our food based on hydrogen production, right? So, I mean, that's a big chunk, about 25, 30% of hydrogen consumption. The other large fraction is refineries, petrochemical refineries. So Ken is exactly right that most of the hydrogen used today is industrial, little for transportation, frankly. And I think in the future, that 70 million tons of hydrogen per year, we hope it gets to about 1 billion tons per year, because we need that hydrogen for decarbonizing the very difficult sectors to decarbonize, which is industrial heat and steel production, concrete production. We need a fuel to be able to do that, because we cannot do everything with cheap electricity. So I think that's where the hydrogen, the big use of the hydrogen is going to be. And that's why we need a, you know, I think someone asked about the cost of hydrogen production, and that cost for carbon-free hydrogen has to come down by a factor of 2 or 3 to compete with the carbon-based hydrogen production that has CO2 emissions. And so there's a lot of research that is needed for both the cost reduction and sort of mobility of hydrogen, as well, moving hydrogen from one place to the other. And we can get into that discussion later on.
Okay.
Yes, thank you very much. Yeah, so that you mentioned, there were actually quite a few questions about transport. I don't mean vehicle, but the transport of hydrogen. And so, for example, Japan has few primary energy sources. So hydrogen, which is a secondary energy source, should also be imported from overseas, as shown in the presentation. But isn't it difficult to import hydrogen because of its low volumetric density? There's also a question about LCA. What is LCA of liquefying lignites in Australia and bringing it to Japan? Or there's also questions asking, isn't it better to, if using brown coal, isn't it better to import brown coal instead of degasification inside Japan? So we can take a question at a time. So, but I think in general, the question is, how do you bring hydrogen to Japan, and what is the cost and LCA of it?
Yes, yes. In the early stage of this project, the KHI, Kawasaki Heavy Industry, they estimated the CIF cost at the port, CIF cost to be about 30 yen per normal cubic meters, so correspond to about $3 per kilogram hydrogen. Okay, so even if we include the extra energy, extra cost for the liquefier and the gas fire, we can realize the cost to be about $3 per kilogram in the future. Not now. This year is just starting the demonstration project.
There was actually a question. Go ahead.
LCA analysis has been done by many people. Okay.
Do other panelists have comment on this?
I have a comment on the if we import the hydrogen in a liquid basis, so yeah, I think the liquefaction cost is quite expensive. Like I think by rough calculation, the minimum work for liquefaction will be that almost 10% of the HHV, higher heating value.
Or more.
Or more. Yeah, I mean that I mentioned about the theoretical work. Therefore, the actual work is, I think, 2 or 3 times more, at least. Then, so the important thing is how to recover the cold energy is one issue when we import, especially in Japan. Japan must import in the form of liquid hydrogen, maybe. So,
the so-called low temperature exergy. Okay, how to use the low temperature exergy in Japan side is quite important. First, we try to use the low temperature exergy to make the pure hydrogen for the hydrogen oxygen. To make the pure oxygen, to separate oxygen from the atmosphere, to realize hydrogen and pure oxygen gas turbine system. But through the actual precise consideration, calculation, it's impossible. So, but low temperature exergy can enhance the turbine efficiency by the, how to say, intermediate cooling system in the gas turbine. Okay. For that purpose, you can take it.
After intercooler of the
intercooler. Oh yes, it's intercooler. For that purpose, low temperature energy or exergy can be effectively used to increase the overall efficiency. Okay, but still we are discussing about that.
Yeah, for some thoughts on hydrogen infrastructure and moving hydrogen. The way I look at it is there are 2 sides. One is on land and the other is over oceans. On land, and we all talk about moving hydrogen, but the biggest challenge, and I'll only give the US perspective, the biggest challenge is to build the infrastructure of pipelines to move hydrogen. This is not just a technical issue. There are hydrogen embrittlement issues that we need to address, but it's just the issue of logistics, of permitting, of NIMBY, all kinds of challenges. So on land, the best way to move hydrogen is to move electrons and figure out how to produce cheap hydrogen by water splitting with the electrolyzers that Ken talked about. And the cost of the capex of the electrolyzers has to come down by a factor of 2 to 3 to make that hydrogen cheap enough, carbon-free hydrogen cheap enough. The other way to move hydrogen with existing infrastructure is methane. It's natural gas pipelines, and then use methane to produce the hydrogen, because the great way to move hydrogen is by CH4. And so there is steam methane reforming, and there's which is existing. Then if you do the carbon capture of steam methane reforming, the cost is going to be about $1.50 to $2 a kilogram, somewhere there. And that's the competition for any other ways to produce hydrogen. So that's the existing technology. And now there's research going in my lab on methane pyrolysis. So if you can produce hydrogen and produce solid carbon, that's much, much easier to handle than CO2. And maybe if you can make carbon fibers, you could use it for other applications. And there's a sort of two revenue approaches. The question really comes up, what about moving hydrogen across oceans? Today's infrastructure, I mean, there's a cost associated with hydrogen that Ken talked about, but the infrastructure to move large amounts of hydrogen today exists in LNG, okay? And once you move LNG, you can then reform it to produce hydrogen in your local entity and then distribute it. And I think that in terms of just infrastructure cost and the time, that LNG infrastructure already exists and much easier to move it that way. Not to say that we should not be building liquid hydrogen ships, but that will be complementary and has to compete with existing LNG infrastructure to move large amounts of fuel.
But the temperature level is so much different. Liquid hydrogen, the temperature is minus 253 degree, 100 degree lower than the liquid natural gas. Yeah. So technology is somewhat different, including the heat insulating process also.
But it's much easier. It's much easier to move LNG than to move liquid hydrogen.
Oh, why?
Because the technology already exists. It's already going on right now. LNG is being moved from different parts of the world, right? So
anyway, Arun said many things, very important things. But to distribute hydrogen on land, we have no pipelines in Japan, but the US, you have many pipelines, natural gas pipelines. So add the hydrogen into the natural gas pipelines is one possibility. Another one is combine the hydrogen, CO2-free hydrogen and CO2 to form the methane, and then use the existing infrastructure of gas pipelines. But what I am most interested in is the direct conversion from methane to solid carbon and hydrogen, as you said. Arun, you said about that.
That's right. That's right.
Solid carbon.
Yeah. I mean, it's been around to make carbon black for a long time.
Yeah.
There's a company called Monolith out here that is doing methane pyrolysis.
Not only carbon black, other some sophisticated structure could be also possible.
Right. Exactly.
Yeah.
So and in fact, right now we have an ARPA-E project to take methane and produce hydrogen and carbon nanotubes at scale.
Yeah. And this kind of subject I like.
Right. Because then the United States doesn't produce enough carbon fibers. In fact, most of the carbon fibers we import from Japan. And so if we can build using our own natural gas, produce hydrogen, carbon-free hydrogen, and make carbon fibers, that has implications in the auto industry and many other industries.
Yeah.
I think that's very sort of great discussion for young people who are listening to this webinar. I think they're looking for sort of technical challenges that they could contribute to this scene. I think that was really great.
And also fundamental.
Fundamental science. I'm sure a lot of people are interested in the fundamental science, chemistry, and so on. Let me just switch gear a little bit. I think we also have getting some questions about the safety issues of hydrogen technology. For example, Luke Richard Higgins, what are the safety requirements, concerns associated with hydrogen vehicle? Are there currently classifications for testing these certification of these vehicles? And there's an anonymous question asking questions related to storage safety for large-scale hydrogen. How to ensure the safety of vehicle, airplane, loaded with flammable hydrogen gas, which could also make hydrogen vehicle airplane costlier to engineer and slower to win public acceptance. So maybe either Yasu or Ken, maybe you can start.
Regarding Safety?
Safety.
Mhm.
I think it's safety if we do not have any accident.
But before we discuss about that, we have to know the difference between explosion and burning. Okay?
Funny, yeah.
Burning velocity is very small, less than 1 meter per second. And explosion has very high speed, higher than the sound speed. When we solve this kind of problem theoretically, we can have two eigenvalues. One eigenvalue correspond to the normal propagating flame, less than 1 meter per second. The other solution, the other eigenvalue correspond to the detonation explosion, which has higher the velocity higher than the sound speed. So many public people misunderstand the difference between explosion and flame propagation. Okay, so burning and explosion are different phenomena based on the very fundamental standpoint. Okay, and then
as Ken
we discuss.
Yeah, as Ken mentioned, the speed of sound of hydrogen is very fast. I think 4 times higher than methane.
Yeah.
Therefore, if there is a crack, so leak rate is very fast, and the inside temperature decreases, rapidly, more rapidly than natural gas. Even if we have a same pressure, initial pressure in the tank.
Yeah.
So if therefore for safety, I don't have any how do you say I'm okay with hydrogen, but many people doesn't like, okay, because Ken mentioned we when we are getting the hydrogen vehicle, we are sitting on the high pressure tank. Not so.
But the Toyota, before Toyota introduced the fuel cell vehicle into market, of course, they did the test for safety. Okay, so Toyota people said that even if the big collision collide with other vehicles, when the car itself is totally destroyed, but hydrogen tank remains as it was. They said they did the test to keep the safety, of course.
Can I just add just one more comment? I completely agree with what Ken and Yasu said. Any energy stored has safety issue. Okay, anything stored. You take a lithium-ion battery. In fact, the oxidizer is already there.
Of course, I agree.
Yes. And so I think one has to look at it comprehensively as to, in a lithium-ion battery, you don't even need outside air. The fuel and everything, you have a short circuit lithium-ion battery, you're going to catch fire.
Yeah.
So, but that, there's technology that has been developed to keep it safe. And yes, there are a few accidents here and there, but there's a huge amount of attention spent for safety. The same thing in fuel tanks, in gasoline fuel tanks. I mean, recall in the 70s and 80s, the gasoline tanks were blowing up in some of the cars. And that, people have spent time to make them safe. So I think safety is a technical issue, number one, but it's also a societal acceptance issue that it is going to be safe. Right?
Yeah.
Great discussion. So we're also getting, I think some of that was mentioned already during the discussion, but we're getting a lot of questions about the hydrogen propulsion, direct propulsion, I think, using hydrogen. Peter Godard, why fuel cells and not just run H2 into existing internal combustion-based engines and generators? Can we instead convert internal combustion energy vehicles to run on H2 and convert Honda diesel generators to run on H2, for example, and so on? Yes. So could any of you comment on this using hydrogen for propulsion?
Propulsion mean, for airplane?
Vehicle
Vehicle.
or even, yeah, internal combustion engine, for example, vehicles, or I guess airplane can be one of the examples too.
I think the combustion is different. Premixed, hydrogen combustion is different from premixed, methane or other natural gas combustion. So the flame, as Ken was pointing out, the flame speeds are different. So the burner design has to be different. And so it's not that it cannot be done, but we need to adapt to the fact that it's a different fuel, and the reactions and the reaction kinetics are different. And as a result, the system has to be modified.
Well, more than 20 years ago, 1990s, the BMW actually developed the hydrogen combustion, internal combustion engine, and successfully ran in the Munich city. I drove by also in Munich, okay. But the hydrogen consumption is not so large. So liquid hydrogen, if we keep the liquid hydrogen for a long time, the liquid hydrogen will boil off. Okay. So at this stage, the liquid hydrogen internal combustion engine using liquid hydrogen by BM disappeared now. But BMW has very deep and high level experiences about that.
Yeah, so do you have any comments on this?
Yeah, I have a question to Ken about the efficiency of the internal combustion engine, hydrogen car, and also the fuel cell vehicle. If you compare the efficiency, which is advantageous? Maybe fuel cell vehicle, right?
Of course, fuel cell vehicle has a higher efficiency.
Higher efficiency.
Yes, much higher efficiency, I think. Yeah.
How many? Maybe 40%.
But oh yeah, the internal combustion engine has used to be having efficiency of about 14%. But 14%. But it used to be okay. Now the high efficiency vehicles coming out, so the internal combustion engine efficiency is coming up very rapidly, nearly more than 40% now. So difference is becoming very smaller and smaller. Okay.
So
yeah, still fuel cell vehicle has a higher efficiency, but the difference is becoming smaller and smaller.
Yeah, that's what I thought. I mean, just a question for Ken. The octane number of hydrogen is more than 130, right? It's like 135, 140 or so, which means even with spark ignition engines, you can go up to higher compression ratio without knocking. And if that's the case, you should be able to get pretty high efficiency with higher compression ratio. Even with spark ignition, you don't need compression ignition.
Yeah. So to increase the to realize the higher efficiency for internal combustion engine, hydrogen internal combustion engine is very active. I have no experience on that, but competing fuel cell higher efficiency, engine higher efficiency, and competing. Okay. And in the future, both should be important. Arun, agree?
Yeah, I think the benefit of having the engine is that the capex is much lower, and so if the efficiency becomes competitive, the operating cost is for the same amount of energy, power and energy is roughly then becomes the same. So the capex will determine. And so the capital cost of the engine is much lower. Now, having said that, there are hydrogen embrittlement issues that we should not forget. And we still don't understand fully what is hydrogen embrittlement, how it works. So there are these other issues that, and someone said about 20% in introducing hydrogen in natural gas pipelines. It is true, you could do that. We still don't completely understand what the impact of that is going to be on the lifetimes of the pipeline. And because we don't completely understand hydrogen embrittlement. And so this is scientific issues that are still wide open for our students and postdocs to look at.
Yeah, I think that's a very great comment. And I think it's very encouraging. Okay, so we're getting, I'm very happy to see that a lot of people are positively impressed by the spread of household NFR. But at the same time, people are asking, what is the dollar per kilowatt or dollar per watt for the household generator or the cogenerator? And I think we had this discussion with Gan before the session, and you didn't really know the numbers. I just want to ask the audience now. I'm sure there are Japanese researchers in the audience. If you know what dollar per kilowatt NFR gives, please raise your hand so that we're going to pull you up on the stage.
I'm not sure because the private, the stationary fuel cell cogeneration system in the private houses has to producing heat and electricity. So we cannot discriminate how many percentage for electricity, how many percentage of energy goes to heat. It's not so easy to separate. We can discuss the total amount of energy consumption. Okay. So one reason is I'm not careful to measure the payment. Okay. Always my wife did. So another reason is the separate of heat, the cost of heat and electricity is not so easy. And in general, the electricity output is maximum less than 1 kilowatt. It's not enough for the usual house. Okay. So mixing of electricity and heat, we have to discuss the combining both, but I cannot say the correct number. But what I can say now is lower the energy cost, including heat and electricity, lower than the existing energy. I can say
very much.
But I can say all. That's all.
So I think we're we're running out of time. But for this question, we will ask people who know. Professor Shikazono at University of Tokyo probably may know, and post the answers to the YouTube through Ganchen. Okay.
Oh, please.
All right. So before closing, I think we have about 3 minutes left or so. I just want to make sure that all the panelists have said everything you wanted to say. So why don't we just take turn and make concluding remarks, let's say. Maybe we'll finish with Ken, and maybe we can start with Yasu. Would you like to make some comments for the overall discussion?
Thank you very much. I was so excited with this great event, and I enjoyed the discussions with Ken and Arun. Hydrogen is, as Ken mentioned, it's a secondary energy. So, therefore, so I think that we have to make use hydrogen with higher efficiency. So otherwise, we cannot we will not be able to have a hydrogen society as Ken define. That is my. So therefore, maybe so we need many great efforts to increase the efficiency of each element. Okay. That is my comment. Okay.
Thank you very much. Thank you. Arun?
Sure. So first of all, let me just make some general remarks. Whenever we talk about energy and we want to make decisions about strategies, it has to be based on a balance between the economy, between the environment, and national security. If you ignore one of them, it'll come to bite you at some point in the future. So I'm so glad Ken mentioned security, because we often forget that in an academic discussion. And so that's number one. Number two is that when we look at something like hydrogen, which is going to be a secondary energy, we got to look at it as a whole system. In the generation side, in the mobility, moving large amounts of energy across the world and across land and ocean, and the use of the hydrogen. And there are greenhouse gas emissions in all of them. So there's a question of economics, of cost. Cost really matters. And in fact, much of the R&D goes into actually reducing the cost. But there's also CO2 and greenhouse gas emissions. And so we have to look at that holistically at all of these sectors, the generation and this competition out there, moving hydrogen, and then moving hydrogen in the broadest sense of the word is moving energy. And then you could convert that to hydrogen later on. And then the use of the hydrogen and the most efficient use of the hydrogen. And in all of this, again, economics matter, and where that energy comes from internationally, controls the geopolitics of the 21st century. So we have to look at that holistically and think about strategies and and in terms of research in all of these, whether it is the generation side with low cost, greenhouse gas emission free hydrogen, moving side, and the use, there's research opportunities galore. So I wish I was now an undergraduate or graduate student getting into this field, because this is going to be one of the most exciting times of research in energy, and in particular in hydrogen.
Thank you very much. Great comment. Ken, do you want to close?
Yeah, Arun said everything. Yeah, I am always saying the same to the student and to others. We have to look at every different part of including the economics and the environment, the cost, and so. But Arun, I definitely agree with Arun. But finally, I'd like to say that we still have many very scientific fundamental subject to do, as the direct conversion from methane to carbon material and such like that. Okay, so not only the overview, but also I like to come back to the fundamental research again. But really, I appreciate all of you. I really enjoyed talking with you and Paul and the questions. Thank you very much.
And Jun, thank you for doing a fantastic job in just managing the whole discussion. Appreciate it.
My pleasure. Okay, so let me just, before really closing, let me pull up my slide, or their slide, to wrap up. Sorry, I was supposed to do this now, the announcement for the next webinar, but I did this already, so I'm going to be really quick. So there'll be next week, was it next week? Or maybe the week after. 19th of August, there'll be this webinar on thermal management of electric vehicle, new energy engineering challenge. And then also their future events. Now, let me wrap up. Please type in your suggestions for future. So we'll keep the Q&A mode open for another 5 minutes or so. So please type in your suggestions for future events, speakers, topics, and format. And please sign up on email lists for future notice. And past events, videos, and Q&A are on this website. Okay, so please, with that, we would like to close this webinar. Thank you very much, Professor Ken Okazaki, Professor Yasuyuki Takata, Professor Arun Majumdar. Thank you very much. And thank you all for listening. And good morning, good afternoon, good night. Thank you.